Hello, I'm Takashi Tanaka from the University of Texas at Austin. In this video, I will present an overview of my NSF career project titled Directed Information Theory for Networked Control Systems in Big Data Regime. This project is about networked control systems, which generally refer to control systems comprised of multiple decision-making components that exchange information over a communication network. Designing such systems could be a challenging task when the communication resources available in the network is limited. So the main mission for the network control systems theory is to provide a design guideline that makes systematic and intelligent designs possible. Network control systems have been studied very actively since 1990s. However, because of the fast evolution of network technologies, it is important that the research focuses has to be constantly redefined. So looking ahead, the future technologies, what will be the role of network control systems theory in the next decade? To have some intuition, let's take a look at the connected car concept, an example of network control systems. Here, I listed up 3 technical challenges that must be addressed before this concept becomes a reality. Thinking about these challenges gives us a hint on what kind of problems we should study. The first technical challenge is the unprecedented size of real-time data that must be shared over the network. And this is largely because of the recent popularity of AI-based control algorithms. These algorithms is becoming, because of this algorithm, it is becoming commonplace for the required data rate to exceed the available communication resources. And this is despite the fact that 5G technologies will increase the communication bandwidth by orders of magnitude. Essentially, this is because the network demand is expected to grow at even a faster rate. The second challenge is that there are multiple users. This makes the data rate issue even more difficult. So what we need to resolve this situation is a methodology to design information flows among agents properly, sometimes prioritize some communication links over the others, so as not to overwhelm the network while keeping the system functioning. Unfortunately, this is not a trivial task. So in this picture, I'm showing here is a simple simulation study we performed recently. So in this study, we tried to identify the best data rate allocation for B2B communication links so that the fuel consumption of the entire platoon is minimized while the desired level of string stability is maintained. So what we found was that the system performance can be significantly improved by properly designing information flows. And this was possible even without increasing the total communication resources. And that was an interesting result. But another lessons we learned from this study was that currently there are no systematic methods or optimal information flow design. So the only approach we can take is essentially trial and errors. And finally, there's an increasing concern about privacy. By privacy, I don't necessarily mean privacy of individual drivers. I claim that automakers also have privacy that must be protected. A couple of years ago, there was an interesting web article titled "Connected Car Data is a New Oil," which essentially says that automakers will soon be able to make more money by selling vehicle data than selling actual vehicles. And if this is true, then automakers will be strongly discouraged from sharing driving data with other vehicles because this means essentially losing money. And if the automakers do not participate, the connected car concept will never become a reality. How to design a network control system in such a way that privacy is preserved is a real issue. So what kind of theoretical tools do we have to address these issues? For the data size issue, fortunately, we have a pretty mature field of data compression. However, what I want to emphasize here is that the baseline theory for data compression is not intended to be used in control systems. For example, if we look at the rate distortion theory, which is essentially the baseline theory for lossy data compression, it is very difficult to generalize it to the situation with causality and feedback. And even even a bigger problem is that the current lossy data compression theory does not tell you what kind of information you should discard. In the rate distortion theory, the distortion function, which essentially tells what kind of information to be prioritized, must be given by a user. So in the connected car example, it is essentially your responsibility to select which information to be prioritized. And again, this is not a trivial task at all. In order to accommodate multiple users, there are efforts from both information theory and control theory communities. Unfortunately, it is very difficult to combine these tools because underlying assumptions are very different in these fields. In information theory, essentially real-timeness is less prioritized, while in control, real-timeness is a critical requirement. However, discussing the notion of data rate in a framework of classical control is very difficult. So, in terms of the baseball terminology, the problem of network control systems is like a so-called Texas Leaguer's hit. This is a seemingly an easy pop fly that essentially both information theorists and control theorists fail to catch. For privacy, we have both cryptographic and non-cryptographic methods, which are both studied in the control community recently. However, there has been no consensus on how to define privacy mathematically, especially when it is difficult to keep track on private information propagation over dynamical systems in a very complicated manner. So in this career project, we'd like to develop a new theoretical tool that can be used to address these problems more systematically. So the purpose of this career project is to develop a novel tool for system-level information flow optimization to address these issues that I just described. Unfortunately, information flow is not like water flow. It is not so obvious how to quantify it. As a promising approach, we propose to use the concept of directed information, which I will introduce momentarily. So from now on, I'd like to briefly explain the baseline theory, which will serve as a building block to solve more advanced problems in this project. Suppose we have a discrete time stochastic control system like this. Every time step, the system output is compressed by the encoder, converted into a binary code word, and then transmitted to the controller. We assume that this communication channel is digital, but noiseless. In this problem, we want to design a tuple of encoder, codebook, and controller that achieves a certain control performance, let's say gamma. Among the ones that satisfies this control performance, we want to find the one that minimizes the expected code word length in order to reduce the communication cost. And since the required communication cost is a function of the required control performance, this function, which I called the operationally defined trade-off curve, will look like this in this picture. And this function essentially captures the trade-off between the control performance and the required data rate. Unfortunately, computing this trade-off curve exactly is a very difficult task. So we have to look for an approach to approximate it. Luckily, the concept of directed information turns out to be very useful here, which I will explain next. Directed information is an information theoretic quantity that can be understood as a measure of information flow from one random process to another random process. Here, I'm using the definition introduced in the information theory literature, but equivalent concepts have been independently developed in statistics literature, causality measure. So how do we use this concept to solve our problem? To that end, let's consider this entire block containing both encoder and decoder as a state feedback policy P. And in this problem, we are essentially interested in finding a state feedback policy P that achieves the desired control performance and then minimizes the directed information from X to U. The function Ri we defined this way essentially characterizes the trade-off between the required control performance and the minimum data rate, minimum directed information needed to achieve that performance. Then, interestingly, this function Ri turns out to be a good approximation of the trade-off curve, trade-off function that we are truly interested in, as we introduced in the previous slide. More precisely, as shown in this figure, directed information provides a lower bound of the achievable data rate. So this suggests the following strategy for the optimal information flow design for networked control systems. So let's keep considering this kind of single encoder, single controller system just for simplicity, although eventually we are interested in analyzing more complex systems in the future. We are interested in finding a pair of data encoder and controller that achieves the desired control performance with minimum communication cost. But unfortunately, as we saw, solving this problem directly is very difficult. So we propose to approximate this original problem with the one involving directed information instead, and solve this problem, obtain a solution, and use this solution as a guideline to reconstruct an encoder-controller pair here. And this may end up giving a suboptimal solution to the original problem, but we hope that this is a good enough solution to be practical. So now you may doubt if solving this auxiliary problem is any easier than solving the original problem. Fortunately, it turns out that this is the case. In case of the linear quadratic Gaussian problems, this auxiliary problem can be solved quite beautifully. So I want to mention that too in the next slide. So let's assume that the dynamical system you consider is linear, and the control performance is measured by this kind of quadratic function. And we are interested in finding the decision law that minimizes the directed information from X to U. It turns out that the optimal policy solving this problem can be realized by a sequential connection of 3 linear data processing units. The first block is the perception unit. This unit makes a noisy observation Y of the state vector X. In an information theoretic viewpoint, this unit plays an important role of reducing data rate. The output from this block is processed by Kalman filter and then by the certainty equivalence controller and then fed back to the system. We call this structural result the 3-stage separation theorem because essentially there are 3 data processing units in this architecture. Now, what's surprising about this result is that those design parameters C, sigma V, and K, they can be found by solving a convex optimization problems. And this essentially becomes a semi-definite programming problem as shown here. So by solving this optimization problem, those parameters can be reconstructed. So this way we can essentially compute the optimal policy that minimizes directed information with an aid of semi-definite programming. And once we find the policy that minimizes directed information, we can post-process that result to obtain a suboptimal encoder-controller pair that solves the original problem. I would not go into the detail of this picture, but this architecture essentially involves the optimally selected metrics C and K that are both obtained from the SDP solution, as well as the optimally selected quantizer step size delta, which is also obtained from the SDP solution. Now that we have a baseline theory for simple network control systems involving point-to-point communication channel, now I'd like to talk about ongoing research. In Thrust 1, we are trying to make the directed information approach more scalable in order to accommodate big data. In this first task, we are essentially trying to expand the LQG result that I just explained so that we can deal with a much bigger state space. Unfortunately, SDP does not scale well, so we are investigating into alternative approaches. We are also considering minimum directed information control problems for nonlinear systems. Since there's no convenient structural result like separation theorems, totally different approaches are needed here. Some of the recent results are summarized in our recent TAC paper, but more results will come in the near future. We're also trying to accommodate situations with unknown dynamics by considering adaptive source coding. And then in Thrust 2, we consider how to generalize the directed information method that I just described to multi-terminal communication networks. In this first task, we are investigating into the theoretical connections to network information theory. But at the same time, we are also studying more heuristic approaches. In this ACC, we are actually presenting one result regarding data rate resource allocation for dynamic data fusion, which is related to this research thrust. And finally, in Thrust 3, we tackle privacy issues. In the first paper, we discuss a kind of interesting result that follows. We use directed information as a privacy metric. We are also studying privacy preserving control and reinforcement learning schemes using homomorphic encryption. To summarize, in my career project, we are trying to develop a new framework of networked control systems theory using directed information as a main vehicle. We want to develop a systematic approach to design optimal information flow, which we hope is useful in the future developments of networked control systems. And using this opportunity, I'm also trying to lower the disciplinary barrier between the information theory and control communities. To a certain degree, I believe that this barrier is artificially created because these two subjects are seldom taught together. So as part of this effort, I'm actually developing a graduate level course on networked control systems, which I hope helps to lower this barrier. Finally, I'd like to thank NSF for supporting this project. Also, using this opportunity, I'd like to thank the panel members who reviewed my career proposal and for giving me this encouraging comments. And finally, I'd like to express my sincere thanks to Dr. Baheri for being positive always and cheering me even after my proposals were declined. I believe there are many, many professors in the United States and in this community who have similar experiences of mine. So it's my great honor and my great pleasure to join his club. And with that, I'd like to end my presentation. Thank you for listening.